Hi everybody, this video today is going to cover the back page of the real roots of polynomials. This first section, actually, we've talked about this before. It's talking about bends and bounces, and we've talked about that before. But the main thing I want to talk about from this page is the rational root theorem as well as the irrational root theorem. So the rational root theorem is kind of, I don't know, it's kind of different. We're going to look at P over Q and find what the roots of this could be. And so I'm just going to tell you about it, and then I'll kind of tell you how it's useful along the way. This is the P. This is the Q. In other words, I need to look at the 2 and the negative 25. I don't really care about the ones in the middle for now. Now, 2 has factors of 1 and 2, and that's all. Those are the only factors that go in. 25, it could be 1 times 25, or it could be 5 times 5. What this does for us is, if we couldn't graph it, if we didn't have a graphing calculator, how would we know what the roots are? Well, we could just take random guesses, but that would take forever, right? So instead of taking random guesses, what this allows us to do is it makes some educated guesses. What we do is we look at all the factors of P. P is on the top. And so that is 1, 25, and 5. So some of our possible roots would be positive and negative 1, positive and negative 5, positive and negative 25. Because those are here, that means those numbers might possibly go into it. And in other words, I said it, but I didn't write it. That would be positive and negative. This would be positive and negative. Then we also have to consider the Q. So 1 over 1 is 1. 25 over 1 is 25. 5 over 1 is 5. Now we have to put them all over 2 also. So it could be positive and negative 1/2. It could be positive and negative 5 over 2. Or it could be positive and negative 25 over 2. So those are the possibilities. I don't know what the actual answers are, but these are the possibilities. What we are going to do now is we're going to put this into our graphing calculator and kind of look and see where it might hit. So get your graphing calculator and plug this into your graphing calculator. Okay, here's my graphing calculator. I put in my function. Also on your graphing calculator, make sure that your plots are off. As you look at mine, these are off. If they were on, I'll go up and show you. You arrow up. If it was like blackened out like that, that means that it's on and I need to turn it off. And the way you turn it off is you go up until you're on top of it like that, and you hit enter, and then you get down off of it. So you need to turn off those plots if they are on. And then, like I said, this is the graph that we have. This is the equation. I'm going to go in and graph this. To graph it, I have to go to Zoom Standard, and that's 6. Your calculator might be at a different zoom level if you had graphed something different before this. So you have to go to Zoom Standard. Okay, as I do this, I can see that I have a 0 here at negative 1, and negative 1 is on my list. I also have one at positive 1. Positive 1 is also on my list. This, I don't know. It looks maybe like it's 2.5. I just don't know exactly. And then 1, 2, 3, 4, 5, it looks like it goes through 5 also, which is also on my list. Now, one thing we can do is we can look at the table. If you want to look at the table, you go to Second, Table. Oh, I'm counting by pies. All right, so if yours is just counting 0, 1, 2, 3, 4, you're good. If yours is counting random things like me, you have to change it. So it says press plus for change in table. So I'm going to press plus, and I just want to change it by 1. So I'm going to hit 1, enter. All right, now I can see that I do have a 0 at 1, I do have another one at negative 1, and I do have one at 5. Now I didn't count by 0.5s. I could, and I'd show you that. To do that, I'm going to go to plus, change in table 0.5, enter. So 1, 2.5, and then if I scroll down, scroll up, I've got one at negative 1, and if I go down to 5, I should have one there as well. And there it is. Okay, this theorem, I will have to tell you, it's a little bit, well, partly it is if you didn't have a graphing calculator. But we all have graphing calculators now, so then what? Well, then it's just understanding what possible roots you might have or not. Let me just show you what we need to do for this. So we just went to our graph, and we decided from the graph that both +1 and -1 were on the graph, and 5, but it was only the +5, and probably 5/2, and honestly, I don't remember if it was positive or negative. I think it was positive 5/2. So what we need to do with this information is we need to prove that. So yeah, we came up with it on our list. Yeah, we looked at it on our calculator, but can you actually prove it? And the way we would prove it is we would use synthetic division. So take a second to set up your synthetic division. Of course, you could also do long division. It's just that I think long division, like a lot of you said when I asked about this question, a lot of you said you prefer long division because you know it. But a lot of you mentioned, although you could see that this is shorter, and it is. So I'm going to go ahead and do this. So I multiply that, I get 2, that's a -13. That is -13, and that's 10. That is 10, and that's 25. So that's 25, and the remainder is 0. Okay, you know when you have a big number, like let me just pick any random, I'm going to pick like 144. And you want to say what goes in there. Well, you go, okay, I could divide by 2, and that would give me 72. And then I could say, well, does 3 go in? Well, you don't have to go back to 144. You can take this divided by 3 to see if it goes in. I just bring that up because now, as I'm here with my long division, or my synthetic division, I don't have to go back to the original. I can start dividing again from here. Let me tell you what I mean. A minute ago, we said 1 was a 0, and we also thought that -1 was a 0. I'm going to pick up here. I'm not going to go back to the original. So that gives me a -2, which is -15, and that's now a +15, which is 25, and that's a -25, which is 0. Okay, again, goes in evenly. Has a remainder of 0 means goes in evenly. Okay, this 5/2, which is 2.5, I'm going to hold that one for the last. I'm going to go back and do this one because I feel like it's easier. Honestly, I can't remember if it was +5 or -5, so I'm going to look. On my graph, it is +5, so I'm going to do a +5. So I'm putting a +5 over here, and that is 2, 10, -5, -25, and that is 0. All right, remember how I said I was going to save that 2.5 or 5/2? Here it is. Remember that whatever your, whatever the stuff is down here, this is of course your remainder. This 5 is just like 5 minus 5, and this is your x. So this is actually representing 2x minus 5. That's what that actually means right there. Well, why do we care about that? Well, our factored form now, instead of having this long thing, which this long thing, there's nothing wrong with it, but it's the standard form, we could write it out as x minus 1, x plus 1, x minus 5, and 2x minus 5. And remember that 2x minus 5, that's like actually 2.5. That's what that means. And then it had up here, we had equals 0. So we can put equals 0 just so we have it. Okay, so what this does is this is kind of tying two things together. It's tying together the synthetic division, tying it to the graph, which also ties it to the x-intercepts, and then the possible roots are which ones could possibly work. Because if you didn't have a graphing calculator and you had to divide in forever and ever, that would be a pain. Okay, we'll talk more about this and the significance of it for this class, but let's go on to the next example. First of all, this one we just did was called the rational root theorem. All of these are rational numbers. They are integers, or the numbers that can be expressed as fractions. That's what a rational number is. Down here we have irrational root theorem. Irrational numbers are numbers that cannot be expressed as a fraction. They are like numbers that repeat forever, like pi or square root of 2. So what do we do when we have irrational roots? Well, we're going to do the same thing. And this maybe will show us a little bit better what the applications of this are. That is, we're going to take p and q. Of course, the factors of 2 are just 1 and 2. The factors of 4, it could be 1 times 4, or it could be 2 times 2. Back to the rational root theorem for just a second. We put p over q. That is the whole numbers on the top, or excuse me, the last term on the top, the first term on the bottom. So we just have to remember that. Because here's what we're going to do. We're going to find the rational roots first, and then we're going to find the irrational roots. Okay, Our rational roots come from the list of these numbers, 1, 2, and 4, as well as all of each of those over, so that was over 1 over 1, 4 over 1, 2 over 1, and then we also have 1 over 2, 2 over 2, and 4 over 2. But of course, 2 over 2 is just 1, and that's already on our list, so we don't need to put that one. 4 over 2 is just 2, and that's already on our list too, so we don't need those. So what we have now is we have our list of possible rational roots. And we can go back to our calculator and put this in our calculator, put this equation into our calculator. So I'm going to do that. So I'm going to clear out the equation I had before. And if you don't know how to do the exponents, it's this number above the division bar, it's that caret, and that gives you up and then 3. And then you have to arrow off of the caret and minus 3x squared. And remember, minus is different from negative, so it's minus 3x squared. And there's an x squared there right by the 7. Minus 10x. Okay, so I have mine entered into my calculator. I'm going to go to Zoom Standard, that's 6. Okay, here is where that list comes into play. I don't know if you can tell, but none of these really appears to go through an integer, right? Like right here, there's an integer, but it's not going through it. And right here, there's an integer, but it's not going through it either. This one here is not going through an integer, but maybe it's negative 1/2. And negative 1/2 was on our list. I'm going to go to the table, second table, and see if negative 1/2 is on my list. Yeah, it is. Negative 1/2 is a 0. But I need to prove that because that's what we do in math. We show our work. So I'm going to go back to my paper. All right, so I'm going to set up my synthetic division with 2, negative 3, negative 10, negative 4, and a negative 1/2 here in the corner because that was my 0. Bring down my 2. Negative 1/2 times 2 is negative 1. That's negative 4. That's a positive 2. That's a negative 8. That's a positive 4. And a remainder of 0. Okay, at this point what we have is 2x squared minus 4x minus 8. How'd I get that? Well, this is my constant, doesn't have an x with it. This is x to the first, this is x to the second. I need to factor this. Well, one thing is I can see there's a GCF. Let me factor out that GCF and see if that helps me to factor down the rest of it. All right, this actually cannot be factored. There's no way to factor this down. So what I have to do, I have to use a quadratic formula. Okay, so I put in my numbers into the quadratic formula. Notice that when I did this, I was using these numbers. You can use them from up here, but it just is easier, I think. These are smaller numbers, so I chose these. But you'll come up with the exact same answer either way you go. Okay, I'm going to put this into my graphing into my calculator. Actually, I don't want to use my graphing calculator for this, and the reason I don't is I want exact answers. So let me tell you what I mean. I'm just going to simplify everything without using my. I'm not looking for a decimal. I'm looking for an exact answer. Okay, so when I go through and simplify my quadratic formula, that's 4 plus 16, which is 20. Square root of 20. 4 goes in there, and the 4 is a perfect square, so that's 2 radical 5. Last step is when you have this, you can divide everything by 2, and so you get this. All right, what the irrational root theorem is going to say is, it says, saying they have to come in pairs, which we kind of know, hopefully, because the quadratic formula has a plus and minus into it, but it's just saying if 1 plus radical 5 is a root, then so is 1 minus radical 5. And how this could come into play into a question is, like maybe I had some long polynomial and I said that 2 plus radical 3 is a root, then you would have, and I'd say, then what's another one? And you'd say, well, 2 minus radical 3 must be the other one, because they go in pairs. Anytime you have an irrational number like this, they go in pairs, as far as roots go. All right, when we come back to class, we're going to work on some things with rational roots as well as irrational roots. Please write down questions if you have them. Write them down somewhere so that when you come back to class, you know to ask those questions. Okay, I'll see you in class.